So before we start the course, I would just like to say a few things, not about details about how many points you get and click, but what's the general idea of what this course is about. It's probably unlike any other Coursera course that you have seen. And it's very ambitious. The general idea is this. Suppose you're a scientist of some kind, economist, physicist, mechanical engineer, chemist, and you have a problem. Typically, this kind of thing happens to graduate students. You have a problem, and what you have is a mathematical description of your problem. So there is some bunch of equations in front of you. 3 equations, 6, etc. And you don't know what they really do. So you put them on a computer, and you observe that what they do seems very complex. It might look turbulent, in the sense that clouds are turbulent. It might look chaotic in the sense that after a very short time, it seems like you're not predicting anything. The outcomes look random. So what do? The first part of the course is based on ideas of Poincaré. 120, 130 years ago, he faced a similar problem. He had Newton's equations of motions. Very simple. They describe the celestial firmament. So there is sun, there are planets. And at that time, there was a proof, quote unquote, by Laplace that the solar system, so collections of the planets that we see, is eternal, that Newton laws will just move planets around and they'll just keep doing their thing like they do today. Poincaré set out to prove that this is either true or false, and he realized that what one has to understand first is not the details of these equations, but the qualitative theory of possible motions that such equations could describe, or what kind of consequences your particular law, your particular equations that describe evolution in time, that's what we mean by word dynamics. Dynamo is motion. And what Poincaré said is that what we have to do is we have to organize all possible motions. We have to have some sense of the geometry of chaotic motions, which is where all possible outcomes lie and how they interrelated. Now, this is easy to say, but typical problem that a researcher faces today tends to be very high-dimensional. And our intuition fails us already in 4 dimensions, but typical problems in chemistry might have 12, or neuroscience, they might have 12 dimensions, they might have 100 dimensions. If you're interested in fluids and turbulence, in principle have infinitely many dimensions. And in computations, you have 100 to million dimensions. So it's easy to say, count all possible things that happen and how they're interrelated, but how are you going to do this when dimensions are so humongous? So the tool that we will use, the step 2 of our course, is technically called the ergodic theory. Don't be afraid of the word ergodic. It's a very crazy misnomer due to Boltzmann. But you have to have a sense for all states of possible outcomes that your laws of motion can produce. And you have to have a scheme of naming them systematically and enumerating them systematically. That's called symbolic dynamics or qualitative dynamics. At this point, the things start getting very much like statistical mechanics. What we do in statistical mechanics, which, by the way, Einstein was the master of, what we do in statistical mechanics is enumerate possible states or configurations of our system, and then we learn how to average over these configurations and produce predictions. It turns out the chaotic or turbulent dynamics works exactly the same way. You have to start partitioning the state of all possible outcomes into neighborhoods. And once you learn how to do this, we'll get to the next part, We will now learn how to use first the geometry of space, second, its partition in the neighborhoods. And folding these two things together, there is a predictive scheme. We'll be able to produce the formulas analytic, but the data you need to use are computational. We'll be able to predict things that you could possibly not predict with any computer where you're not thinking before doing this. Now, about the course itself. So that's the grand scheme. The course itself is experimental in the following sense. Most online courses today are called MOOCs. They're massive. This one is called a SOOC, which means a small open online course. It's now this word in Danish, I happen to be Danish, has a meaning. It's called suk, and it means a sigh. So I personally, every morning, wake up with a sigh or suk, and I say, what would Brad Pitt do in my situation? Because myself and my friends, we have not been trained to be television anything. You have to understand, I've never owned a television set in my life. So this is a very 19th century undertaking. The core of this course is a book. It's called Chaos Book. You can click on it on chaosbook.org, and you can download it for free. It's under Creative Commons license, so you can steal but not plagiarize. You can read it online for free. All the associated programs, links, etc. are all open source, open to anybody on this planet, and currently only this planet. This book is not supplementary material to videos in the course, like the custom is in MOOCs. It's the other way around. The idea is you're supposed to read the book. As a graduate student, maybe you form a little study group with some other graduate students. And as you read it, you might just enjoy reading it and be done, but you might find it useful to click on the link to a video. Video like this one with a talking head, or maybe video like this one, where one works out in detail some part of an equation, or talks to you while doing this. And then we pick up a new term, which essentially says, if I had some kind of cigar here, it stretches, that's the first term, but along the trajectory, every place I get a kick, and once I get a noisy kick, that also stretches. So there is an integral from t0 to t. Or somebody shows up with silly glasses and a microphone on them. You know, silly wig, Uber glasses, I got them for free. And that's something that will wake you up for a moment. And when they come back, they'll be exactly the same distance. So along the flow, for a periodic orbit, not for a general trajectory, only for periodic orbit, there is no shearing at all. Intervals have exactly the same size. And these eigenvalues are telling you what the shearing is. So there is always eigenvalue 1 for periodic orbit. But this is really just auxiliary. We are told today that people find it useful to stare at television-like explanations of things. But you will actually, to make any progress in this course, will have to read the book, and in particular, and that's very important, read the examples. Examples in the book are worked out examples. They're like problem sets, but somebody has actually gone through the pain of going through them. And then, more important still, if you are serious about this course, you will have to work out problem sets. Because this is modern times, it's not sufficient to know about Bessel functions of second kind and have pencil and paper. You should know that too, but you'll actually have to compute, because there is no other way to develop any intuition about dynamics, about complicated motions through large dimensional state spaces, There's no other way to do it than by computation. This is the reason why this is a modern subject. Even the basic ideas were formulated 140 years ago. Computation by itself should be kept under moderation, though. Historically, meaning last 30 years, the mindless computation has actually held the subject back rather than helped it. This subject has very beautiful ideas, which are largely unknown to physics, applied math, and other communities which should know them. My experience is this: unless I get somebody into my office and I explain it on the blackboard, they don't get it. It doesn't matter that I have written it in the book and rewritten in the book. No matter how I rewrite it, they'll never get it. So my personal motivation is that if I combine the book, maybe, and if I twiddle on it either on the blackboard or on some kind of tablet to help you get through difficult parts, that maybe I will get across to some young, impressionable minds. The idea is this: now we're in the third millennium, everybody is stroking their smart devices. Maybe this is the way to reach these young, impressionable minds.
And you have labels.
Yeah. So if we look at the expanding term.
So, to summarize, we have nothing to offer but blood, sweat, and tears